Morning, everybody. It's I would like to thank the organizers for inviting me today. It means a lot for me to be present for this special conference in honor of Cyrano. I wanted just to mention that I had many occasions to interact with him over the years. Already, as soon as I started working on spin glasses, and it happened also that we had some very nice moments together because we shared the Ampere Prize of the Academy of Science in 1996. And I discovered yesterday, trying to find back the date, I discovered that the year before was Claudie Sixon. So, and of course, there are several people in the audience who also received this prize. I'm particularly proud of it. And we shared office with Cyrano here. I was a regular visitor for several years, and it was a great pleasure. I want to talk today about statistical inference. I will not spend much time defining what it is. There has been a talk by Lenka yesterday, I think, on this topic. I will just say loosely that statistical inference means trying to infer a hidden rule. It may be a hidden probability distribution, or hidden values of variables from data. And what is the big challenge in statistical inference these days is the case in which you have many parameters that you want to guess. In a Bayesian formulation of statistical inference, you are naturally mapped to a problem of statistical physics in which you want to find a phase which is a kind of crystal phase, and I will try to explain that. It happens that in many problems, the best solution so far is based on sophisticated Meanfield type algorithms. It's some kind of long-term elaboration on what was called in 1987 the cavity method that we developed with at that time with Giorgio and Miguel Virasoro. And but the main results of the last few years is that this cavity method that was used as a tool to find the phase diagram, to understand the phase transitions and so on, it can be turned into a very powerful algorithm. And that's what I want to explain. So I will just give, so that people have an idea of what it is about, I will give one example without working out in all details, but just to mention. Imagine that you are doing some growth of a phase, a binary sample in which you have a phase A, which is in white, which grows in a black phase B. You have a sample, and you want to know how it is. What is the pattern? What you do typically is that you take the sample and you shine a synchrotron line on it. And here you put the camera, you have a certain number of pixels, you measure the intensity of the light which has been going through the sample. And if the absorption coefficient in the two phases is different, then you get a number here on each pixel, and this number basically tells you what is the fraction of the phase of each type. Okay? Now, knowing these fractions, you cannot reconstruct the sample. That's obvious. It may happen that all the white are on white side, and so on and so forth. What is typically done at the synchrotron is that if you have here L pixels simultaneously, what you will do is that you will rotate the sample and do measurements at various angles. And typically what is done is that you do L angles. It means that for each angle you have L measurements, you have L square measurements. And from these L square measurements, you are able to reconstruct the L square pixels by what is called an inverse Radon transform, which is like a kind of Fourier transform in some sense. That is, having all these angles, all these measurements are enough information to get the result. Now, imagine that we are looking at a sample, which is the case here actually, in which the domain size, the typical domain size, is much larger than the pixel. You have a relatively large correlation. Then it happens, for instance, this sample is, I don't remember, 1,000 by 1,000 pixels. It is clear that there is not 1 million bits of information in this sample. There is much less because of the correlation length. And actually, you could even invent a short description of this sample, which would not be look at each pixel and say, this is black, this is black, this is black. It would be very boring, but just looking at the position of the interface, for instance. That's much better. much more efficient. And in itself, it tells you that the information that is contained in this information is much less than 1 million bits. So can you, the challenge, one of the frontiers of information theory at this moment is what is called compressed sensing. In compressed sensing, what you want to do is to try to retrieve the information, the full information on this sample, by doing a number of measurements which is less than the number of unknowns. And in this case, it should be possible. And actually, it is possible. It is possible to reconstruct this picture instead of doing measurements on 1,000 angles, to measure it only on 16 angles and get it back fully. And in order to do that, you need to set up a statistical physics framework in which, or Bayesian framework, in which you need to have some prior. And the prior in this case is the fact that you know that you are looking at the binary mixture, and that you have some pattern, and you assume that there will be some kind of correlation length which is much larger than the system size, than the pixel size, sorry. So you need to set up a here I will have a system, for instance, of just Ising spins representing the binary mixture up or down for each phase. And then basically the measurement will tell you that the light which goes through will tell me what is the average of all the spins which is in this band, for instance. And now the challenge that you have is that on one hand you have a lot of measurements, and for each measurement you have measured a certain value. It gives you the sum of the spins along the line. But then you need the prior. And the prior in this case is very easy. You just use a prior that tells you, I want to have spins that such that neighboring spins are correlated. So you put an Ising prior. And you can either, if you have some knowledge of the correlation length of your sample, you will pick up the J appropriately, or you can even learn it. I will not elaborate on that. So using this prior knowledge together with the measurements, you turn the problem into a problem of spins with multi-spin constraints. And this is typically what we have been studying using Meanfield equations. It happens that if there are enough measurements, and for this you need these 16 angles that I was saying before, the most probable configuration of spins corresponding to this measure, the ground state of this problem there, is the exact composition of the sample. And for this, you don't need to know to the 1,000 angle. It happens, the transition happens much before. And so this is what I call a crystal. It's not a crystal in the usual sense. It's a crystal, I mean, it's not an homogeneous sample. It would be too easy to guess in some sense. But it is a crystal in the sense that there is one configuration of these spins which has a lower energy than all the other ones. So it's a crystal state. It's the one that Giorgio said that he would stay away from the crystal state, and I would like to focus on that. So it's a very complementary talk to the one of Giorgio. I will focus on the crystal state. So basically what we will do is, what I want to tell you is how Meanfield can be useful for crystal hunting. And it happens that crystal hunting is something that can be quite hard. And I want to give you one other example, very simple, one that you can program now or during the break if you want, if you just want to see what can happen weird. Imagine that you have Ising spins, sigma I, again, but with 3 spin interactions. And these 3 spin interactions, they are of the, years ago it was called the Matisse model. So they are just the product of tau I, tau j, tau k, where tau are themselves. So tau is basically the hidden configuration. It's the crystal. It's the one that I'm seeking. But now what I just have is some configuration of these spins, of the spins which are generated by a Boltzmann measure, taking with this energy. And of course, you see that by a simple gauge transform, I can change all my measure and say that this is just a ferromagnetic sample. I mean, for each triplet, I have the energy is minus Si, Sj, Sk. So this energy is minimized when either all the spins are up or one is up and 2 are down on each triangle. Okay? So you can generate, for instance, a random sample of this Hamiltonian. You take random plaquettes, triangular plaquettes, And of course, the ground state is very easy to find, because once you have realized there is a gauge transformation, well, it's enough that you align all the spins in the new gauge, and all the plaquettes are satisfied. So it's obvious. The result is obvious. Now, is it obvious for the computer? The computer a priori does not know the correct gauge, so he has to guess the right gauge. And so you can do something, which is just look at numerical simulations, do a Monte Carlo. So you take this Hamiltonian, and you start from completely random condition. You don't know that it has that the ground state is ferromagnetic, so you should not bias. Start from a random initial condition, and you simulate, and you decrease the temperature. And what you find is that the energy does something like that, and it stabilizes, it freezes, the system freezes here, and you get this energy. And now, if you insist a bit and you increase the number of Monte Carlo steps, the first line here was 10 to the 4 Monte Carlo steps. Here the bottom one is 10 to the 7. And so what you see is that by increasing the computing power, you get a little bit better. But you are still very far from the true ground state. The true ground state, I know it. I just put all the spin aligned. This was a model with 4 triangles per spin. So the ground state was at energy minus 4/3. It's there. And actually, what I can also do is start from the true ground state and heat it up in my Monte Carlo. And what I will find is that I stay at this very close to this energy, and then at some point there is a first order transition, and it becomes liquid. So here I have a system which is, I told you you can simulate it during the break. It's basically correct. In this system, you have the liquid phase, you have the glass phase, which is here. And actually, it can be shown in this case that even if you increase the number of Monte Carlo steps, you will not go beyond a threshold which is very close to that, unless you do a number of steps which is exponentially large in the size of the system, which is impossible. And here you have the crystal state. And basically, crystal hunting is this thing, finding this, while the natural physics of the system freezes at much higher energy. And this is, in this case, with 100,000 spin, it's a very large difference, of course. So I would like to tell you a little bit how this can be done with Meanfield-based algorithms. And let me do a brief history of Meanfield equations, starting from Weiss beta piers, going through the Meanfield equation. So these are very simple, and in some sense, usually people say, well, it's Meanfield, so it's trivial. It is trivial, but as Giorgio's talk has shown just before, it has turned into an extremely sophisticated tool when you develop it in the framework of disordered systems. And so there are basically in physics, you have the homogeneous case and the glassy cases, which are very complicated. But the use as an algorithm, it's interesting in itself that it was used and as I said, it's basically using this cavity method or the Thoresen-Anderson-Palmer equation as an algorithm. It developed in our community relatively recently, but it developed in parallel in other communities. Gallagher used it for error correcting codes already quite long ago, and Pearl used it for general constraint satisfaction problem. So I will basically spare you, or just say in 5 seconds, the 111 years ago Meanfield method of Weiss, basically looking at the magnetization as function of an external magnetic field, a computation that had been done by Langevin just before. And Weiss say, okay, if the field consists of an external magnetic field plus an internally generated magnetic field generated by the other ones, then even in the absence of an external field, we have this self-consistent equation. It depends only on 2 parameters, M0 and alpha, and he turned to do the experiment on magnetit and found a wonderful fit. Okay, that was easy. Now, basically this idea, if you turn it into a general case, it would amount to say that the local magnetization is the response to the field, and the response in this case for Ising field, Ising spins, it's a tangent function. So it's a tangent of the inverse temperature times the local field, but you take the average of the local field. That's typically the Weiss computation. it's obvious if in general in disordered systems these equations are useless. They are bad in the sense that they neglect the fluctuations. The correct formula is that the local magnetization is the expectation value of the tangent of the local field, and substituting the expectation value of the tangent by the tangent of the expectation value is as we all know, is an approximation which in general is rather bad. So 83 years ago, Bethe and Peierls did a better job, if I may. I mean, I am full admirer of what Weiss had done. So I mean, and they proposed to do something slightly different and to look at the central spin and look and solve exactly for the magnetization of the central spin in presence of its nearest neighbors, but assuming that the nearest neighbors themselves are independent. And so this amounts to erasing this other part of the graph and assuming that the part of the graph just amounts to a local field acting on these fields here. You can do this exercise. It's a 2 lines exercise, and you find in the homogeneous case you find a new Meanfield equation, which actually gives a better value of the critical temperature. It has also one very nice advantage that in this case it gives the exact solution in 1 dimension, and so it predicts that there is no transition in 1 dimension correctly, which was not the case of the naive Meanfield. So in the case of a disordered system, you can adapt this Bethe-Peierls ID. They did not do it that way, but it's easy to adapt. And you say that there will be a local field acting on this spin k in the absence of I. So it's a local field due to the external world, the rest of the spins that I have not drawn. The same thing here, local field acting on j in the absence of I, etc., etc. And then you can solve easily for this system of 4 spins here. And again, I spare you the computation. And basically what you get are these equations here. That is, you find that you can close the equation on a set of local magnetic fields. And these local magnetic fields, they are typically cavity fields. They are the fields, again, HK/I, this thing here, is a local field acting on K if I cancel the interaction between K and I. So it's due to the rest of the world. Okay? And now basically what you say is that if you know the local field acting on this guy, the local field acting on this guy in the absence of J, you can compute the local field acting on I by a recursion formula. So you have closed equations on a set of variables which now are no longer the local magnetization, but they are cavity fields which live on the edges, basically, which are the influence of K towards I. And so this is called, this can be turned into an equation. It can be turned into an algorithm. Basically, your algorithm now, if you have a disordered system, it is to say, well, for every edge, every interaction of spins on my graph, there will be a local field. This local field, it's in computer science, it's called a message. It's a message passing equation. And basically, you compute the new message sent from I to J. It depends on the messages that have been received by I. And you iterate that. This gives a number of coupled equations for the cavity field. And the belief propagation algorithm, it happens that Bethe-Peierls and belief propagation have the same initials, so I always use BP. It's very comfortable. Of course, Bethe-Peierls never really wrote the equations for the disordered case, but I mean the spirit of the method is there. These BP equations, they are n-edge coupled equations for the cavity fields. And basically, in general, what you just do is you iterate them. That is, you take the 2 incoming fields, for instance, if you have connectivity 3, take 2 incoming fields, generate the new ones, and so on. And you can update it in parallel, in series, and so on. There are many ways of doing that. And this BP has been something which has been very much used. It is the one that was used, for instance, in error correcting codes by Gallagher. Still now, if you look at the new generation of codes, which are called LDPC code, They are error correcting codes for transmitting information and correcting the noise that you transmit. And these are based on basically spin systems with multi-spin interactions. The same thing that I gave you as an example at the beginning. And they are best decoded by iterative equations, which are of this type. When is simple mean field? When are these various mean field equations exact? Okay, simple mean field is very easy. Everybody knows it is exact in one case, which is a Curie-Weiss model, in which you have long-range interactions, which are all ferromagnetic. That's easy. In that case, it happens that the local field becomes the fluctuations of the local field can be neglected, and so it becomes exact. When is belief propagation exact? So belief propagations are these new mean field equations. They are exact in several circumstances. They are exact in one dimension because it's basically a rephrasing of the transfer matrix. You can interpret it as a transfer matrix. It's exact on a tree. It happens that the only hypothesis that is done when you do the BP, when you write the BP equations, the main hypothesis is the fact that you suppose that the spins K, J, and L, which are here, if you erase I, if you erase all the central part of the graph, that these three spins are uncorrelated. So if your interaction is on a line, that's obviously true. If it is on a tree, it's also true. You erase the central part of the tree and you have branches that are uncorrelated. It is also exact in a case which is interesting, which is locally tree-like graphs. That is, imagine that you have Erdős-Rényi graph. Then it happens that the size of the loop going from this guy to this other guy can become very large, typically of order log n. And so if you erase I, the distance between the spin j and the spin k becomes large. It's a large distance of order log n. And now, if the correlations decay at large distance, then you can neglect the correlations between j and k, and the BP equations become exact. So that's at the heart of why we have been using these equations in many problems. Of course, it relies on this hypothesis that you have a decay of the correlations. So this happens either when you are at in high temperature phases, or if you are in low temperature phase but remain in one phase. Within one pure state, the correlation decay at large distances. Let me mention three important developments of these ideas. One is the special case of infinite range models. If you have an infinite range and disordered model, the SK model, where the j's are over 1 over square root of n, then if you stay within one pure state, the correlations can be neglected, and you write the belief propagation equation. And it turns out that, first of all, you can use the fact that the j are small, so you can expand that. And then you can also notice that the fact of summing over all the neighbors but one, because there are n neighbors, it's a very small correction. You can work out this correction perturbatively. I will not do it. But then you find, after a few lines of computation, you find these equations here for the local field, or this HI is the local magnetic field, times beta HI is the local magnetization. And these are the celebrated Thouless-Anderson-Palmer equations. They are here derived by the detour through BP, and in my opinion, it's by far the best way to derive the TAP equation. Because the original TAP paper was kind of difficult to follow or something. It mentions an appendix that was never published and so on. I mean, that was... Okay, and so these are TAP equations. So they have been around for a lot of time, for a long time, and they were very well known as a very bad algorithm. So there is something that was missing, and actually there was a small trick that was missing, which was found relatively recently. It's the iteration time. That is, if you look at the iteration of BP, you say the new message is at time t plus 1 is computed from the old message at time t, and you turn that into the TAP equation, you find that the new local field at time t plus 1 depends on the local field at time t and the local field at time t minus 1. It's because there is this indirect interaction. You have the spin which interacts with its neighbor and interacts with the other at time previous. And using these correct time indices, they turn out to converge and become much more efficient. What happens if the elementary variables, if the elementary spins are not binary variables or discrete variables, but they are continuous? That was mentioned also in Giorgio's talk, and certainly in Lenka's talk yesterday, I imagine. Well, then life is a bit more complicated. If the local variable is not a spin, but it is a real number or a complex number, whatever you like, well, basically you can write the same equation, the same type of equation, but now what matters is what is the probability distribution of this guy in absence of I? Well, what it is, it's a function, it's a distribution for a variable, which maybe say it's a real variable. So you have a distribution P, the probability of the variable xk in absence of I. Okay. And basically the BP equation, they map into something. You take two probability distribution, the one of k, here there should be, there should be k, j, k and l, yes, that's correct. You have the one on k and the one on l, and you find the one of I by okay. You can write explicitly this function. I did not want to put big formulas on the screen, but they are very explicit. Now, of course, implementing that is kind of heavy, because it means that on each edge of the graph, you have a probability distribution. So you can decide, you put a histogram, you put a sample, there are many ways of doing things, and we've been playing with that. There is at least one case in which it is easy. It's the case where the connectivity is relatively large, so that basically you can assume that this local probability distribution is approximately Gaussian. And this is called approximate message passing or generalized approximate message passing. There is a big literature at the moment in information theory working with all these algorithms. So they have all new names. I mean, I don't recognize neither the cavity method, nor the beta piles, nor the TAP. But once you have the dictionary, it's easy to see. And then the last point is what happens in a glass phase when there are many pure states. When you have many pure states, basically, I told you these equations are correct if you have a locally tree-like graph, only in the case in which you are within one pure state, because you need that in absence of I, you need the correlation between these two spins are small. And basically, what happens if you have a glassy landscape, it means that you will have many pure states, and for each of these pure states, there will be a solution for these equations. So you have a lot of solutions, and that's normal, because the local magnetization for this state are very different from the local magnetization in this other state. The overlap is, in general, very small. And so basically, in this case, what you have to do, if you have an exponential number of states that happens in many of these systems, is you have to do statistics over the many states. And that is what is called survey propagation. And survey propagation is just, you look at the statistics of this local field over the many states, and you write again a recursion equation for these statistics. It looks complicated. It is a bit complicated. Still, technically, in problems like the satisfiability problem that Giorgio has mentioned, in random satisfiability, this is still the best algorithm that we know. It has been around for 15 years as the best algorithm that we know. So, it means that there is really something deep in the fact that having understood the phase structure, the fact that there are many states, can be turned into a much more efficient algorithm for this problem. Now, I would like to spend the last 10 minutes on an extension of this idea of Meanfield equations. And there is one challenge which is ahead of us, which has been touched in various contexts, but not systematically yet, which is what happened to these Meanfield equations when the disorder is correlated. So far, I was discussing what happens in the case in which the disorder, let's say the interaction between the spins, are random variables, but they are uncorrelated. Now, what happens in the case of correlation? And we have one very nice example of that has been around for many years, which is the Hopfield model. So let me just recall the definition of the Hopfield model. The Hopfield model is a model of spins, n binary spins, seen as a caricature of a neuron. Si, the spin number I, is either +1 or -1. One thinks of Si equal 1 as the fact that the neuron sends an action potential. Si equal -1 is a neuron that would be quiet. And you have patterns to be memorized. You have a certain number of patterns that you want to memorize in a system of neuron like that. And the Hopfield model, as it was defined originally, it just consists of n binary spins and a certain number of patterns. And each pattern is again a configuration of spins. It's a special configuration. And the idea is that if you design the model well, you will have this pattern, and the dynamics, the dynamics of the spin system, let's say Monte Carlo or whatever kind of dynamics that you would like to do, for instance Meanfield, will converge towards the pattern. So it means that you will have memorized a certain number of patterns with basins of attraction, capacity to correct errors, and capacity to organize a memory in a way which is very different from the standard memories used in computers so far. So Hopfield they proposed to study the Hebb rule. In the Hebb rule, you just have the coupling constants between the spins, Jij, which is a superposition. It's a superposition of Matisse model, basically. You take the Matisse model with the gauge corresponding to pattern 1, and then you add the one corresponding to pattern 2, and so on and so forth. If the number of patterns is small, this works very beautifully, because there is no interference, and so that's easy. If the number of patterns becomes extensive, of the same order as the number of neurons, then the phase diagram is a bit more complicated, and basically the phase diagram is the following one. You have here the temperature, and here the parameter should be called alpha, which is the number of patterns divided by the number of neurons. And at high temperature, you have a paramagnetic phase. At low temperature, and if you do not have too many patterns, you have what is called a retrieval phase. It means that the Hopfield model is working the way that we wanted it to have. We have local minima which correspond to the memorized patterns. And then here we have a mess. We have a phase when the temperature is intermediate, or when the number of patterns is too large. You have a spin glass phase in which the retrieval is no longer possible, and the Hopfield model does not work. In this case, it turns out that, as you saw, the coupling constants are built from superposition of patterns. So they are no longer independent variables. And that creates a complication to writing the Meanfield equations. And so let me spend a couple of slides explaining how you can derive the tap equations for the Hopfield model. The naive thing would be to say, well, in the end, this guy is just a kind of spin glass. So I have the Meanfield equation for the spin glass. I write the tap equations. They are here. And this should give me the correct result. This is wrong. This is wrong for the following reason, that basically the tap equation, they tell you that you look at the magnetization of this guy, and you take into account the indirect interaction of I that polarizes J that retropolarizes I, roughly speaking. And you neglect further retroactions. And that is correct in the SK model. That is correct when the J's are uncorrelated. And you can see that diagrammatically. But in the Hopfield model, you have some, the J have some structure like that, and they are correlated. So it means that if you look at I which polarizes J, which polarizes K, which polarizes I, the value of this diagram depends on the product Jij, JJK, JKI. And there is a correlation. So this product is no longer zero. They are not independent. So because of that, you cannot write the naive tap equations. The right way of writing, the correct way of writing tap equation is the following. I will not discuss the full mathematics, but basically you can look at the Boltzmann measure for the type of patterns of coupling that are here, and you find that the Boltzmann measure can be written as the sum of the spins exponential of this quantity square. And this quantity is the projection of the spins toward the pattern. So you write basically the Hamiltonian in terms of the local projection towards each of the patterns. Easy, that's just an identity. And of course, this being a square, you can disentangle the square by a Hubert-Sratanovich Gaussian transform, which is here. So you have local variable lambda mu and spins Si. And basically, you have the lambda mu are real variable with a Gaussian measure. The spin Si are binary. And the only interaction term is this one. It's an interaction of the spin and this projection variable through the pattern Xi I mu. Technically, you can draw things like that. You have a number of spin variables, which are the original variables, the neurons. You have these auxiliary variables, lambda mu. They are the projections toward the patterns. And each spin has interaction with each pattern, with each projection variable through the pattern Xi I mu. Okay? Now, the beauty of writing it this way is that you have, again, a constraint satisfaction problem in which you have local variables, but now the disorder becomes independent on each edge. And so you can write the belief propagation equation. You can turn the crank, or everything that I said before, spend a few pages, and basically you can find the equations. And the correct equations, these are the belief propagation equation, and you can then simplify them to equations for the local quantities. So this is the local field on the spin. This is a local field on the auxiliary variables, and this is an order parameter. So this is just to say that when you have correlated disorder, you cannot write the naive Meanfield equation. You have to go to something more sophisticated. This equation, just for the explaining that they may be not as trivial as they look. They were first written in the book with Giorgio and Miguel in '87. We never published it in a paper. And several times in the next year they were claimed wrong. But now it has been established that they are just correct. So, I mean, and they can be used as an algorithm. That is, you can put the correct time iteration indices. You say that this is at time t plus 1, t plus 1, t minus 1. And you iterate that, and you find and that's a nice way of iterating. So one slight elaboration on that I worked on last year is the following. I am very much interested in, for reasons that will appear clear later on at the end of the talk, I am interested in the case in which the patterns that you want to memorize, they are not structureless, but they have a special structure. And the special structure that I find particularly interesting is the case of what I call combinatorial structure. A combinatorial structure is a pattern which is built from the superposition of elementary ingredients that I call features. That is, you have a database of features, and then each pattern will be built by composing from various features. So imagine that you have on your set of features, you have a plate, you will have the fruits of the table, and so on. And then you will decide that you take 4 of them and 1 plate, and it builds a table. Or you can take other of these pieces with complements, and it's a chair, and so on. And I insist a lot. I think that that's something that we collectively had completely missed in the 80s and 90s when we were working a lot on Hopfield model, neural networks, and so on. It is this strong influence of the fact that the patterns are not patterns that you want to memorize in everyday life or in language, in vision, in many of the activities that you want to understand. They are not at all random. And in many cases, they have this kind of combinatorial superposition of elementary features. And of course, when I say that, immediately you can see that the elementary features themselves are combined by sub-features and so on. You can say that there is a hierarchical construction. So now I leave it as an exercise for the break. Maybe this you need a longer break. You look at, again, you can look at the Hopfield model with these kind of patterns. This was the Hopfield model with the auxiliary variables looking at the projection on the pattern. And it is written this way. And again, you can disentangle this last term by another Hubbard-Stratanovich transform. And it turns out that when you do that, you find that there are three types of variables. There are the spins, but the only visible variable, the only one that you have at the beginning. The Hamiltonian is written in terms of spins. But basically, when you Hubbard-Stratanovich it, you find that there are the auxiliary variables which are here, which are the projection toward the pattern. And then there are these guys who are basically the projection toward the features. And then you can write, and then it turns out that now the disorder interaction that sit on all the edges which are here are independent. And so you can turn the crank. You can look at this diagram. You have the three-layer graph, a layer of visible neurons, hidden features, and hidden patterns. And you turn the crank and you write the BP equation, you simplify them, and you find a set of equations that I have not dared to write, involving the local field on the spin, the local field on the features, the local field on the patterns. And they are coupled. So I find it rather interesting that starting from the Hopfield model, that is structureless, a purely fully connected model, if you want to study it and study the Meanfield theory of it and write the correct Meanfield equation, depending on the type of pattern that you want to memorize, you will get to a different structure. So if you have just independent patterns, you get what is called a Boltzmann machine, a restricted Boltzmann machine. And so you just need to add one layer of hidden variables, which are the projection to the pattern. But as soon as you have combinatorial patterns, you have this intermediate layer of features. And this I find somewhat appealing in the sense that, as you may know, there has been in recent years a big progress on deep networks, which are layered networks, in which the information is processed from an original visible set of variables, like an image, and you want to decide at the end whether there is, I think Alenka gave the idea of the cat and the dog probably, or yes. You want to decide whether it is a cat or a dog that is on the image. And the big success has been elaborating on these layered networks by adding more depth into this network. And here what I can see is that spontaneously in this case, what you have to have is a visible input, subfeatures, features, pattern, and so on. So this is not a proof of anything, but I think it's an interesting hint of a trajectory. There are many people, including in the audience, who are trying to understand why deep networks are better. It seems that in deep network there is this possibility of learning the task much more easily than if you just take a two-layer network. And the question is why? And one possibility is that basically the real world, the database that you feed, with which you feed this network, the database that you want to learn, is based, for instance, on images. And these images, they have a combinatorial nature. That is, an image is based on elements which are combined by sub-elements and so on and so forth. And in this case, my impression is that it's related to this database, to the structure of the world, of the task that you want to learn, the reason why you should learn with a multi-layer network. Thank you.
Thank you very much, Marc. Questions? Yes, Kurt.
So this version of the multi-layer networks is not the most general, yes? You got there by, so to say, following a mathematical structure that we like because you see how you compose it elements. But the general multi-layer network would not fit into this pattern.
No, you're perfectly right, and I should emphasize one thing. I mean,
I love this because we can work with it and understand it.
I'm presenting it as a kind of a hint or an analogy or something. Here, I want to stress one thing. I have been working on the simple problem, which is writing the Meanfield equations that give me a closed set of equations for the local polarization of the neurons or the spins. I have not been working on the learning problem. That is, there is the big problem of deep network is when you have a task and it's hidden and you want to find the correct values of the coupling constants and so on, and you want to learn it. The learning problem and the generalization problem, which is the last version. You would like to study the generalization problem, the teacher-student problem, it's so sometimes called. It happens that the two are not completely unrelated, and so I have been focusing only on the first one. So far, I have not been able to generalize to the case of generalization precisely, but I think it's an interesting open challenge.
May I ask a question, a really elementary question? When I listen to mathematicians doing compressed sensing, they don't do statistical method. They analyze it by wavelets or whatever. It's not statistical. So which one is better for?
Oh, I mean, it's not totally true. I mean, there are many ways. Okay, compressed sensing is a long story. The big breakthrough on compressed sensing, when people started to discuss compressed sensing, they decided that they took another way. Actually, they said that basically you have to solve a problem of constraint satisfaction. That is, you have done a certain number of measurements, and you have to find a configuration that is compatible with all these measurements. And basically, the ideal problem that you would like to solve is a problem in which the cost function is minimize the number of violated constraints. That's the usual problem of constraint satisfaction. Instead of doing that, they have turned it into a L1 problem. They have said, I will do an I will look at a linear problem in which the minimum is when the constraint is satisfied, but if it is not satisfied, there is a cost that depends linearly on the variable, on the parameters. This turns the whole problem into a set of linear constraints. And that you can solve by fast algorithm because you have linear programming and so on and so forth. So that is the mainstream in some sense. What we showed in a few years ago, in particular with Lenka, Florent, and several other people, is that there is an alternative, which is to set up a scheme in which it is a Bayesian approach. You said, instead of looking at it as a constraint satisfaction problem, you say, I study a probability distribution for my variables. This probability distribution takes into account a prior, as I was showing for tomography, and constraints. And now I look at what is the most probable configuration. And solving this complicated Bayesian statistical physics constraint problem with message passing, we showed that we can get into a range of parameters in which the L1 solution does not work at all. So it's more powerful. But it has not not done its way through all the mathematicians. I mean, the ones who are fond of L1, they will remain fond of L1 forever. That's our life of scientists.
Okay. Well, if there are no more questions, I'm told that we should gather in the hall for a picture. Thank you.